Okay, so in this video, we are going to be looking at some real life quadratics, right? So we're going to look at two exam questions from the Junior Cert. So we're going to look at real life quadratics. What do we use quadratics for? Well, we use quadratics to primarily model height of an object. So after an object we throw, or maybe like heights of tides or something like that. Usually if a height goes up and down, we kind of usually model a quadratic after it, right? Or another thing we use this for is to model out area of a shape. For example, I have x minus 2 here in x. So here is the area. If I plot that out, I could find the value of x that gives me the biggest area. So optimizing area of, like, say, gardens, fences, boxes, etc. All this stuff. That is what we use quadratics for. So let's get crack-a-lackin'. So this is the 2016 paper. So this question states, the function h of x below gives the approximate height of the water at Howth Harbour on a particular day from 12 noon to 5 p.m. So h of x equals 10x squared minus 50x plus 130. Thing I notice here, the number in front of my x squared is positive. So my graph is going to have a bit of a U shape to it. And that kind of makes sense, right? Because tide, right? So the h of x is the height of the water in centimeters. So we're looking at like the tide or the height of the water throughout the day. So that does make sense. It starts off high, it gets low, and then it increases again. So the tide is in and then the tide is going back out. So it does make sense that it would follow a quadratic shape like this. So draw the graph below where x is the time in hours after 12 noon. So if x is 1, that just means it's 1 hour after noon. Draw the function h of x equals 10x squared minus 50x plus 130 on the axis below for 0 is less than or equal to x was less than or equal to 5. So my inputs here are 0, 1, 2, 3, 4, 5. So we could do a table of values and all that jazz, or we can just use our calculator. I'm going to use my calculator because I don't wanna. So I go here, I click menu setup. I go to table, click 3, type in my function. So it's 10x squared minus 50x plus 130. Then I'm starting with 0, ending with 5, and I'm going up in 1s. And I mistyped something. What did I mistype? I mistyped something, ladies and gentlemen. Oh, I did. See, this is why it's really important to do a little table of values for yourself on paper first. Because if I just whipped all these in, I would have got 0. So, take that away. Muchas apologies. There we go. 0, 130, 190. After 2 hours, the water is 70 centimeters. After 3 hours, it's 70 centimeters. After 4 hours, it's 90. And after 5 hours, it's back to 130. So let's plot these points. So when x is 0, the water is equal to 130. When x is equal, so after 1 hour, the water is 90. After 2 hours, the water is 70. 3 hours, the water is 70. After 4 hours, the water is 90, I believe. And then after 5 hours, the water is at 130. So here is the graph. Now, it's really important. See here, we don't just draw a line across, right? We know, like, a quadratic has a little bit of a bump to it. You know what I mean? It has a little bit of a bump. So you just have to make sure you kind of do a little dip before you connect these points, because it doesn't give me an obvious turning point here. So I just have to, make my own, make sure it follows that kind of U shape. So let's now answer some questions. So use your graph in part A to answer the following questions. Find the height of the water at 12 noon. So at 12 noon, well, x is going to equal to 0, right? When x equals 0, we go up, the water is at 130. So the height is equal to 130 centimeters. Next one, estimate the height of the water at its lowest point, i.e. its minimum value. So my minimum value is around here. So we're going to roughly say like 65, 67. Now anything around then, so the height of the water at its lowest point, h is equal to 65 centimeters roughly. So remember, you do have a margin of error when working with graphs, right? You do have a margin of error. Right, at 12 noon, how long did it take for the water before the water was at its lowest point? So we want to find out how long did it take from for the water to get from this point to this point. How long did it take? Well, it started at noon, so 0, and at 2:30 it got to that point. So 1, 2, 2 and a bit. So 2.5. So how long did it take? 2.5 hours. All right. Now let's look at another question here. This is part C of the question. So the graph on the right shows the approximate height of water in centimeters at Crookhaven on a different day from 12 noon to 6 p.m. The graph is symmetrical. So symmetrical just means if you fold it in half, nothing overlaps. It has a axis of symmetry. So remember them little things in primary school? Like the little like the butterfly thing. You put you make a butterfly on one side, you squeeze like with paint, and you put it over it, and then it's perfectly symmetrical. So that is what symmetrical just means. It just means if I were to fold it over, there'd be no overlap. So on this day, the height of the water at 12 noon was 180 centimeters, and the height of the water at the lowest point on the graph was 0 centimeters. Taking x as the time in hours after noon, the graph of the function is given by ax squared plus bx plus c, where a, b, c are integers, right? So elements of z, real integers. Find the value of c. So c here. So remember, this is always my y-intercept. And where does it cross the y-axis? Well, it crosses the y-axis at y is equal to 180, right? So c is going to be equal to 180. Or what you could have done is let x equal 0 and y is equal to 180, or g of x is equal to 180. So 180 is equal to a times 0 plus b times 0 plus c. 180 is equal to c. Hence or otherwise, find the value of a and the value of b. So this is finding missing coefficients of a function, right? So what we need to do is here, we need to create my own simultaneous equation. So I need 2 more points on this graph. So what 2 points could I find in this graph? Well, I have this point here, right? So this is going to be when x is 6, my function is equal to 180. I can use that point. Then another point I know I can use here is this one, right? Because my graph is symmetrical. That means this point here is going to be 3, right? And then the y value is 0, so the coordinate is going to be 3, 0. So let's use these 2 points now. First one, so x equals 6, y is equal to 180. So 180 is equal to a times 6 squared plus b times 6 plus 180. So we're going to have 180 is equal to 36a plus 6b plus 180. I'm going to subtract 180 from both sides, and I'm going to have 36a plus 6b is equal to 0. And it's going to factor out a 6 here. You don't have to do this, but I'm just feel liking it. Then I'm going to divide across by 6. So I have 6a plus b is equal to 0. That's my first equation. Just make it a bit easier for myself, you know. Next one, x is equal to 3, y is equal to 0. So I have 0 is equal to a times 3 squared plus b times 3 plus c, which is 180. So 0 is equal to 9a plus 3b plus 180. Can I divide across by... I can divide across by 3, I think. I can divide across everything by 3. So if I divide across everything by 3, 0 divided by 3 is 0. 9a divided by 3 is 3a. 3b divided by 3 is b. And 180 divided by 3 is 60. So I'm going to have here 3a plus b is equal to minus 60 because I brought it over. And there's my second equation. So I have 2 equations in terms of a and b. So I'm going to be using simultaneous equations. So simultaneous equations. So 6a plus b is equal to 0. 3a plus b is equal to minus 60. So now we're noticing the fruits of our labour now for dividing across early, because now I both have b's here with the same coefficient. I just need to change the sign. So I'm going to multiply the bottom one by minus 1. I'm going to have 6a plus b equals 0. Minus 3a minus b is equal to 60. That's going to be equal to 3a is equal to 60. Or the b's cancel out. Divide both sides by 3. I get a is equal to 20. And then with simultaneous equations, you sub it back in. So I'm just going to sub it into the first one because why not? 6 times 20 plus b is equal to 0. 120 plus b is equal to 0. Therefore, b is going to equal to minus 120. And there you go. I found the values of a and b. Therefore, the function is given by h of x is equal to 20 x squared, or is it t? We're dealing with t's, are we? No, it's g. G of x equals 20x squared minus 120x plus 180. And there we have it. There we have it. Right. Let's look at the next one now. So this one we're kind of dealing with area and volume. Right. So this is from the 2014 paper. A rectangular site with one side facing a road is to be fenced off. The side facing the road, which does not require fencing, is L meters in length. So they're having something fenced off. They're not fencing the road. I don't know why, but they're not fencing a road, right? So that's L. So therefore, the sides are perpendicular to the road are x meters in length. The length of the fencing that would be used to enclose the rest of the site is 140. Write an expression in terms of x for the length of the side facing the road. So let's just fill in things I know here. Well, I'm dealing with like a rectangle here, so the opposite sides are equal, so that's going to be x, and this is going to be equal to L. And what I know is the entire fencing of the site here, the entire fencing we need is only equal to 140. So x plus L is equal to 140. 2x plus L is equal to 140. L is equal to 140 minus 2x, and that's it. That's all we needed to do. Next one here, show that the area of the site in meters squared is minus 2x squared plus 140x. Well, I have what my length is equal to. So remember, area is equal to length times width. So length times width, well, my length is equal to 140 minus 2x, and then my width is equal to x. Multiplied in, my area is equal to 140x minus 2x squared. And that, it's there, and I have proven it. Bada boom, bada bing. So let f be the function minus 2x squared plus 140x. Evaluate f of x when x equals 0, 10, 20, 30, 40, 50, 60, and 70, right? So you see here we're going up in tens, and we're asked to draw this function. So now, if you got part 2 wrong, you can still do part 3 because they've given you the function we need to plot. So let's get our table of values up and running here. So I have minus 2 x squared, x squared minus 140 x, plus 140x, I should say. So I'm starting at 0, and I'm so I am starting at 0, and can you let me finish off, please? Yeah, starting at 0. There we go. I'm ending at 70, and I'm going up in tens. I'm going up in tens. There we go. There's my table of values there. 0. 10 is equal to 1,200, 20 is equal to 2,000, 30, 2,400, 40, 2,450, 2,060, 1,270, 0. So let's plot this out, shall we? So I have very big numbers on my x-axis and I have very big numbers on my y-axis. So I think I'm going to scale it. And I think I'm going to be going up in thousands on my y-axis maybe. Or maybe 500s or 200s. I think maybe 200s will work the best. And I'm going to be going up in tens on my x-axis. So this is going to be my area. And it's going to be my x values. So I'm now finding different areas of this site, right? When my width of my shape changes, right? So the area will change when I change my width. So if you just look at this here, like here's a little shape I just made, right? Look, you notice when I change the width of it, right? Actually, when I change the width of it, do we agree? Oh, sorry, you can't see it there with the calculator's blocking it. But do you agree here? I have a shape here. But do you agree when I'm changing the width, the area of a shape is going to change? Look, so like if my width is really small, right, my width is changing, right? If my width is really big, my area is changing. So the area changes when we change the width, right? So the area here, x values. So I'm going to say skip up in 3 boxes maybe. 1, 2, 3, 4, 5, 6, 7. And then I'm going to label it in tens. So 10, 20, 30, 40, 50, 60, 70. Then the area. I think well, my maximum, if we go back to my calculator here, my maximum is 2,400. So I might just go up in 200s maybe. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Rats. Okay, I'll go up in 200s. So 200, 400, 600, 800, 1,000, 1,200, 1,400, 1,600, 2,000, 2,200, 2,400, and 2,600, right? It's a bit messy. Now, in fairness, I could have just done 2, 4, 6, 8, 10, 12 and just put hundreds at the side, but, you know, shoulda, coulda, woulda. Right, so let's plot these points. So, my points here are, my first point being 0, 0. So when x is 0, my area is 0. That makes sense. When my width is 0, my shape is going to be 0. That makes sense. 10, 1,200. So when my width is equal to 10, my area is equal to 1,200. When my width is equal to 20, it's equal to 2,000. 30, 2,400. 40, 2,400. 50 is going to be 2,000. 1,200. And then when my width is 70, my area is back equal to 0. So connect these up. Bing. Up. So ding, ding, ding. Remember, right, we don't just go flat across like this, right? We need to create a little bit of a bump. A little bump. Remember, because we're doing with kind of a U shape. We have to have a little bump to it. Right, ding, ding, ding. Again, you'd be way neater than me because I'm drawing on an iPad. You're going to be doing it on pen and paper. Right, there you go. Draw my graph. Make sure you label your axes. Scales are good. Bada boom, bada bing. Full marks. What's the maximum possible area of this site? So, I go to the max here. So that's going to be my max point here. Again, right? Margin of error. Right? You do have some wiggle room here. So I'm just going across and it's going to be roughly... So if each block is worth 200 and it's between one block, it's going to be roughly... The area is roughly going to be equal to 2,500 centimeters squared. Right? Make sure to put your units in. And then... What's the area of the site when the road frontage L is equal to 30. Now, this right being sneaky little snakes, right? Because they expect you, right, to go to 30 on your x-axis and go up and look for that. No, because my x-axis is my x values. We have L is equal to 30. So, if you recall, from part 1, we found L is equal to 140 minus 2x. So now what we do is we let L equal to 30, and then we find the corresponding x value. So that's a really sneaky question. So minus 1100 is equal to minus 2x. Divide both sides by minus 2. I'm going to get x is equal to 55. And then x is equal to 55. I can do that. I go to 55 on here, so it's going to be halfway between 50 and 60. There it is. I go up. Ding. Hits there. Go across. And it hits there. Go across. And the value is going to be equal to 1,600. Right? 1,600. Now again, my graph is a bit poo-poo garbage, but, you know, let's deal with it. Right? So the area of the site when the frontage is equal to 30 is going to be equal to the area is going to be equal to 1,600 centimeters squared. Right? So there we go. There is two types of questions using quadratic. So one with height, one with area. So again, just really the area point here, right? If you want the maximum possible area for that side fencing thing, right, you would, right, use the value that gives you the maximum here, which would be like 32, 33, right? So you make sure x is equal to 32, 33, and then you fill that in with the corresponding values. So if x equals 32 here, let's say, right, I'd have a shape like this. So 32, right? L is equal to 140 minus 2x. It's going to be 140. It's going to be 140 minus 2 times 32. So 76. And it's going to be 76. And this here will give me the maximum possible area for that site. It will give me the biggest amount of space for the dimensions I am allocated. Right, there we go. That was a few real life questions for you, and I hope there was some help, and I'll catch you guys later. Bye.